All right, so the goal today is to work a little bit more with NDSolveValue and NDSolve, which is the older numerical differential equation solver, and in some senses, at least it seems to me by my experimenting, superior to NDSolveValue. NDSolveValue is a little easier to use, but in some ways NDSolve is superior, so we'll talk about that. I'll talk some more about fully decoupled versus partially decoupled linear equations, and maybe go into more detail about an example like that. Then we'll talk about Euler's method in 2 dimensions and relate it to things with existence and uniqueness theorems about 2-dimensional systems of equations. All right, so we've got this section here about using NDSolve and NDSolveValue. Again, so far we've only used NDSolveValue, and again, that is easier to use. And it's newer. It's new with Mathematica version 10 and beyond. We're using version 10 here. And again, the way to do it is this way. You can define your right-hand side functions for your system of differential equations. So this is, again, a Predra-Prey model. F of r comma capital F is the right-hand side function for the dr dt equation, the rabbit equation. You can tell it's the Prey because you've got a negative interaction coefficient there. And little g is the right-hand side function for the df dt equation, the Fox equation. That's the predator because you've got a positive coefficient for the interaction from there. Typically we call the vector field capital F, but because we've already got a capital F here, I call the capital G here. This is a formula that defines the vector field as a list in Mathematica. You can then use NDSolveValue with this kind of syntax. You put the first differential equation here. This is an autonomous system, by the way. If we were to write it by hand in this abstract form, we would write dr dt equals little f of r comma capital F, and df dt equals little g of capital R capital F. That system, first order because it's got 2 first derivatives, no second derivatives at all. And what was I trying to say here? I forgot what I was trying to say.
Autonomous?
It is autonomous, thanks. No t's on the right-hand side. Again, just like we've seen before in Mathematica when you use DSolveValue, now with NDSolveValue, even though it is autonomous, you need to specify to Mathematica that R and F ultimately depend on t by putting the t's in there. When the t's are in those function arguments, it doesn't negate the autonomous nature of the differential equation. Intuitively, in terms of these, the vector field, autonomous systems produce vector fields that are static, that don't change. Whereas when we look at vector fields for non-autonomous systems, those vector fields actually change as time goes by. The vector fields themselves are dependent on time. Anyway, put the differential equations in there, put some initial condition. I picked initial rabbit population of 1, maybe meaning 1,000, for example. And Fox population of 0.1, meaning maybe 0.1000, which would be 100. And you got to pick some time interval. You can't just put a t here. You need to start t at 0 typically, especially well if your initial conditions are at 0, and go up to some positive time. I think it maybe even works in backward time. Even if I included a negative number here, it might work. I suppose I could experiment with that. Let me try putting a negative number here, like -5 or something. Let's see if it works. Well, it kind of works, but evidently in backwards time, the solution goes off to infinity. You see this kind of message. The solution is kind of going off to infinity really rapidly, so, well, if I make this a -4, then I probably won't get that error. So evidently it did work. It says the domain goes from -4 to 10. I can now make a static picture of this solution curve. It's in green there, and I started t at 0 here. I could make it go back to -5 or -4 and probably see more of the picture. If I do that, ready? Watch the green curve. Yep, you see more of it. Going backward time. And now I'm also seeing why, if I continued in backward time, why Evidently, as t goes to minus infinity, or as t decreases, the solution is going to head off to infinity rapidly. If you follow the curve backwards, it comes over here, and evidently it's going to continue down here and go off this way, off to infinity, so to speak. And that's typical behavior for nonlinear systems, is that solutions, if they do go off to infinity, either as t increases or decreases, they go off really rapidly, and in a sense, in a finite amount of time, kind of like an asymptote, in a sense. If you graph them as functions of t, you'd see an asymptote. You're not seeing that kind of graph here, but if you did that, you would see an asymptote. Okay, but that's a static picture. We lose the information about the speed of the curve, and we also in the vector field, the red arrows there, they're scaled down and they're all the same length, so we're not seeing the information about the actual lengths of the vectors in the vector field, which is of course related to the speed of the solution curve. If I make an animation of all this, starting at time 0, now we can see the speed information coming back into play because I'm letting time increase in a relatively smooth fashion. Watch it here. We see different speeds. It speeds up as it goes in this kind of straightaway here, here, and here. And it slows down when it's over here. And generally speaking, as it spirals toward this spiral sink, this equilibrium point is a spiral sink in this case, it's slowing down. The arrow that you see, the magenta arrow, is the actual arrow from the vector field of the right length. How do I know it's the vector from the vector field? Capital G is the vector field, and this code essentially graphs that. And notice that I did not scale this down by the factor. I did not divide this by 5 or 10 to scale it down. Not only is it getting longer and shorter, but evidently it's got the correct length. And the length at any moment in time is the speed of the parametric curve at that moment in time. Again, when I say speed, I mean speed in this picture. I don't mean speeds of rabbits and foxes running around, okay? Talking about the speed of the curve in this picture, and that's the velocity vector for the curve in this picture. And that's true for masses on springs too. When you're looking at the picture and the speed of the curve in the picture, that's not related to the, well, it's not the velocity vector or the speed of the mass itself as it goes back and forth. It's related to the movement of the mass, but it's not the movement itself. In that picture we saw it on Wednesday, we had a y-axis horizontal and a v-axis vertical. All you're doing in following that solution curve is just keeping track of y and v as time goes by, the position and velocity of the mass. You're keeping track of those quantities as time goes by. Why is NDSolve, as opposed to NDSolveValue, sometimes superior? Let's copy and paste this code down here. Let's change it to NDSolve. NDSolve has been around, I believe, as long as Mathematica has been around. Mathematica version 1, which is like 30 years ago. I think NDSolve existed back then. How do you use NDSolve? If I enter this, it gives you a pretty similar looking output, but it is different. It's giving the output as what's called a rule. That is a little different. You see R arrow and F arrow down there, whereas you don't see any arrows or R's and F up here. Because it's given as a rule, it makes plotting the answer more confusing to do. Let's give this a name as well. Let's call it solution. If I want to plot that solution with a parametric curve in a plane with parametric plot, you have to do something kind of funny here. You have to use a couple commands. One is called evaluate, and another one is called the replace all operator, which in Mathematica is denoted by a slash and a dot. And here's the way you would have to do it: is to go x of t, comma y of t, in curly braces as a list, slash dot solution. Go outside of that, evaluate, and then put a comma. T goes from 0 to 20, or -4 to 10, excuse me. And we didn't see a plot at all. That should have worked. Solution. I'm not sure why that didn't work. Let's see. We do see graphs there. Oh, I got to call them R and F. Sorry, that's why. You got to use the same name there. There we go. And you can animate this. But yeah, this is confusing. Evaluate in slash dot, and you got to use an R and an F instead of an X and Y. They have to match the R and the F up here. That's kind of confusing. Seems like NDSolveValue is better to use because I didn't have to bother. If you look right here, I didn't have to bother with the evaluate and the slash dot. It also turns out that when you use NDSolveValue that you do need to, if you want to do a two-dimensional system, you do need to put the solution names inside a list like this, whereas in NDSolve you don't, evidently. I've experimented with this, and it seems like you don't have to do that with NDSolve. You can see you don't have to, whereas you do with the other one. So why is it maybe superior? Why do I claim it's superior in some ways? Well, let me modify this again. And let me name the solution to also include a couple initial conditions as, in a sense, variables for a function, R0 and F0. And what do you think I mean by R0 and F0?
Initial conditions.
Those are going to be the initial values of the rabbit population and the fox population. Instead of 1 and 0.1, it'll be R0 and F0. I tried doing something similar like this with NDSolveValue and it didn't work. I couldn't get it to work. What's my goal in doing this? My goal is going to be to allow myself in my manipulate animation to change the initial conditions. Oh, and sometimes you get those kind of messages. Okay, let's just clear the kernel. That's been happening a lot recently. It seems like mathematics, and it's happening more often. It's got some things in its memory that are messing it up, evidently. Maybe the fact that I've defined solution already, that might be the problem. Let's just clear the memory anyway. Let's put the functions down here again. Okay, now it works. All right. Now let's do the manipulate again. Except I'm using NDSolve instead of NDSolveValue, so I've got to use the evaluate and the slash dot. So it's a bit more of a pain that way. Let's see, I need to do it here. It's one spot. Evaluate RT, comma, F of T in curly braces, slash dot solution R0, comma, F0. That's one thing confusing that I have to do. If I also wanted to draw the arrow for the velocity vector of the vector field, I have to make modifications there too. Maybe for the sake of simplicity, I'll get rid of that. For the sake of time. Don't have double commas though, get rid of that one of those commas. All right, let's see if this works. Oh, I realized I did something wrong right as I entered that. I've got to also say what R0 and F0 are. They're going to be animation parameters. Let's put them after the V here. I'll start R0 out at 1, but let it go down as low as 0.1 or as high as 2. That's the syntax that will do that. I can start F0 at 0.1 and let it go down as low as 0.01 maybe and as high as 1. So I'll get sliders for those things too. Let the B go all the way to the right here. We can change the initial condition. I can change the initial rabbit population. I can increase it. So you see the initial point moving to the right there. I can also increase the initial fox population. I can increase that. You see it going up. It does change the solution curve. Okay, it changes the initial condition, so it's changing the solution curve. So that's a benefit. I can change the initial condition and see different solution curves. I tried that with NDSolveValue and it wasn't working. Okay, and now I'm not sure if there's some way to make it work, but so far if there is, I haven't found it. I've only started using NDSolve in the last few weeks. Okay, NDSolveValue, I should say. Let me show you one last thing before we go on with this same example. Sometimes it's nice to change initial points in the plane, not by moving two separate sliders, but maybe by moving some sort of two-dimensional slider. So you can change them both at the same time. Now there are a couple ways you can do that. The way that's my favorite is to use something called the Locator Command. What I'm going to do here is instead of having the R0 and F0 like this in the animation part of manipulate, I'm going to do the following. I'm going to have an animation parameter I'm going to call PT. PT stands for point. It's going to have an initial value of 1, 0.1. R0 is 1 and F0 is 0.1. And if I outside this curvy brace here, if I put a comma and then the word locator, and then also, I got to make a couple other changes. If I also, for example, as one way of doing this, put curvy braces in here around the R0 and F0, and then down here, put PT. This will do what I want, and what will it do? It will create an animation where B will still be a slider. However, this PT will not be a slider. Instead, it'll be like a crosshairs thing in the picture that you can click on and move around. And as you move that around, because I'm using the locator here, as you move that around, that changes the initial condition by actually sliding that crosshairs around, by moving the mouse. I needed to put the curvy braces up here because PT is a list, a point. And if I wanted to have it in there without doing some other modifications, I needed to have the input of solution be a point. I'll list the two entries. Oops, why is it not working? Oh, what's wrong? Let's see here. Does this one still work? That one still works. PT somewhere else. Okay, this has worked. I'm not sure why it's not working at the moment. Test some things here. Why did it give me that when I entered that?
You need a semicolon after.
Thank you. Right there?
Mm-hmm.
Yep. I gotta separate those lines of code. Actually, semicolons just suppress output, but I do need those as separate lines of code. And without that semicolon, maybe a comma would work too, but semicolon will work for sure. Anyway, here I go. There's the initial one with initial condition 1, 0.1, but now you see that crosshairs there. I can move this around and change the initial condition dynamically. I'm getting errors over there for some unknown reason. The solution's not going off to infinity, so there's something else going on there giving me errors at that point, but when I'm close enough, getting no errors. Okay, so it's the locator that's doing that, but you've got to make appropriate modifications based on the fact that your initial PT, your initial point, is a list of 2 elements, so I need the solution thing here to be a list for the input so that I can put PT into that, like that. There are other ways you can do this, but that's probably the best way. If that's confusing, I'd recommend watching the video again and experimenting with it on your own. Okay, for your project, you will probably be needing to use either NDSolve or NDSolveValue. So it would be good to experiment with it. Probably for the second test, there will be a question related to NDSolve or NDSolveValue as well. All right, let's do another example in more detail than we had time for on Wednesday of a partially decoupled system, linear system. This is something you should be able to do for exam 2, is to solve such a system. Let's make the completely uncoupled part, the fully uncoupled part, or decoupled part, the x equation. So I'm going to make the right-hand side here just involve x and no y's. And we'll make it linear, again, to make it simple, to make it doable, more doable at least. 2x. So that doesn't have any y's in it, so the x equation can be just thought about by itself. It's uncoupled from y. However, I'm going to make the y equation coupled to x, and thus make the system partially decoupled. So we'll make the right-hand side for the dy dt equation involve an x, maybe negative 3x plus 4y. It's a linear system because the right-hand side functions are linear. And with linear systems, you actually don't want any constant terms either. In this class, and in linear algebra, if you're taking that, you don't want linear equations to have any plus constant terms in them. When you do, you give them a different name. They're called affine equations in such a situation. And that's what we want for differential equations. Don't put like a plus 5 there, then it's no longer a linear system. It's a linear system plus a constant in a sense. But we only want to consider linear systems like this. And it is, again, partially decoupled. That equation is completely decoupled from this one, but this one's not from that. As far as finding the general solution, take the one that's uncoupled, and if it's a simple example like this, you can just see what the answer is by inspection. You don't have to bother separating variables even. It's an arbitrary constant, I'll call it k1 times e to the 2t. K1 can be anything. However, k1 would also equal the initial value of x, since e to the 0 is 1. So I also could write it as x0 times e to the 2t. But let's leave it as a k1. Even though the second equation involves both x and y, so you can't just guess the answer, we can find it by substituting this function in for x. So the dy dt equation can be thought of as dy dt equals negative 3k1 e to the 2t plus 4y. And that's a linear equation in y. Is it autonomous? No, it's not autonomous, because you got the t there. It is linear, but it's not homogeneous. You've got this forcing function here. The associated homogeneous equation would be dy dt equals 4y. Get rid of the non-autonomous part, which you can solve by inspection. YH would be k2 e to the 4t, but that's not the general solution of the non-homogeneous equation. I need to guess a particular solution, which again is a little easier to think about if you think about the equation this way. Put the 4y onto the other side as a minus 4y. Think of this now as a linear operator. You're looking for a function whose derivative minus 4 times the function always equals that. Think of k1 as fixed but unspecified. You want to guess something of the form yp equals a times e to the 2t. The a is probably going to depend on k1. Yeah, it will depend on k1. Find the derivative of that. Yp prime is 2a to the 2t. When you substitute this into the left-hand side and simplify, you want to set it equal to the right-hand side and solve for the value of a. That'll make that work for all t. Just do this in my head here. Yp prime has the 2 in front of the a, and I also have to subtract 4 times y, so 4 times a. So ultimately, I'll get a 2a minus 4a. I'll get a negative 2a e to the 2t must equal negative 3k1 e to the 2t. So a must be positive 3/2 times k1. Catch me if I make a mistake. Does that look good? So the general solution of the non-homogeneous equation, this one, is yh plus yp k2 e to the 4t plus back times e to the 2t. It's got 2 arbitrary constants in it, one of which does involve the same k1 as the arbitrary constant in the x equation. Those are the same k1. They have to be the same for this to work. Combine those, and you get a solution that you can write as a parametric curve. You can either write it that way, or you could call it capital Y of t. I'm writing capital Y of t as a vector. Really, when you graph this, you're thinking of it as a point that's getting traced out, though I could draw a position vector if I wanted to. It's not typically done. I could start a vector at the origin and point at this point, and it would like trace the graph. It would be like a pen tracing the graph, the parametric curve in the plane. We don't typically do that, but I could. Write it like this. I wrote it as a point. I could write it as a column vector. Again, we're flexible in how to write it. What if we had an initial value problem? An arbitrary initial value problem, say x of 0 is x sub 0, y of 0 is y sub 0. I already said the x1's got to be the same as the x sub 0. And then if you plug 0 in here and here, you'll get 3/2 k1 plus k2 must equal y0. Since k1 is x0, you'll get 3/2 x0 plus k2 must equal y0. So the k2 must be y0 minus 3/2 x0. You're going to plug it into Mathematica and make a manipulate animation where you allowed x0 and y0 to change. Plugging in x0 there and there, plug in y0 minus 3/2 x0 there. That would allow you to change the initial condition in the correct way. Can I clarify anything there? Question?
For x of t, when you wrote it in that vector y, why did you put negative 3?
Did I make a mistake?
Would it just be the k1 e to 2t?
Yeah, thanks. I don't know why I did that. Why did I do it? So is there a negative?
That's how it is in the dydt part.
Yeah, I was looking there, I guess, or something. Yeah. It was because of the negative 3 here. Maybe I was looking there. Yep. Thanks for catching that. Okay, so you should be able to do that for the test. The next test, exam 2. We are going to also get into chapter 3 before exam 2, and you should be able to do more complicated examples. The first 4 sections probably of chapter 3. Using some other methods we'll talk about, which are called eigenvalues and eigenvectors. All right, for the last bit of time today, I'm going to focus on a pretty interesting system. This system happens to have something called an attracting periodic solution, sometimes also called a limit cycle. It'll be a complicated system of equations that you can't really solve by hand. It'll be nonlinear. So NDSolve or NDSolveValue will have to be used. We will also get a little practice with Euler's method for 2 dimensions and talk about existence and uniqueness for 2-dimensional systems. So here's the example. Actually, this is one of your homework problems for next Monday. It's problem number 5 in section 2.5, and you'll be using Euler's method for this. I'm not going to use Euler's method right away, but we'll eventually get there. Take a look at this code. So the little f function for the system is y plus y squared. Right away you see it's nonlinear. That's the dx dt equation. dx dt equals y plus y squared. It's nonlinear, it's also automatically coupled to the y equation now. The rate of change of x only depends on the y coordinate of the point you're at, not the x coordinate. Kind of interesting. And the dy dt equation comes from this function here. Kind of a strange thing to pick, but I took it from a book, that's what they picked. Negative x plus y over 5 minus xy plus 6/5 y squared. The nonlinearities there come from the y squared term, and also the x times y term is a nonlinear term. Now I'm going to call the vector field capital F like we usually do. So this formula is defining the vector field. If you want to find the equilibrium points, you can set both little f and little g equal to 0 simultaneously and solve that system of equations. You also can set the vector field equal to 0, although, well, this worked. Although you actually would think I have to do this. It still works. Okay. Probably it's safer to do this in general. I'm trying to set the vector field equal to the 0 vector defining equilibrium points. There's only one equilibrium point at the origin. By the way, that's not too hard to figure out by hand either, just by thinking about it. The only way this is going to be 0, well, actually, maybe this is not the complete picture. This will be 0 if y is 1, or 0 or negative 1. If y is 0, the only way this one can be 0 is if x is 0, because of that term there. If y is negative 1, however, maybe there is another value of x that works. Maybe I should have just used the little f and the little g here. Let's try that, see if we get it on the little one. No, I guess that is the only one. If x is negative, if y is negative 1, what does this equation become? G of x comma negative 1. Oh, that's the problem. It evidently simplifies just with the constant 1. That's strange.
You end up with a negative x plus x.
Oh, okay, you'll get a negative 1 there, which makes this a plus x. Yeah, okay. So that's an atypical kind of thing to happen, but it does happen here. Meaning 0, 0 is the only equilibrium point. All right, here I'm using NDSolveValue in the way I showed you how to do before to get an approximation of the solutions. And you should realize, I mentioned this already, NDSolveValue is just approximating solutions. It's not giving you a formula. It's giving you data plus an interpolation method to connect the dots. But it matches the true solution curve pretty well. It does a good job. So that would take proof. So I'm using NDSolve to get those interpolating functions and then graph them. And it is a pretty interesting graph here. And what do we have here? A very interesting behavior for this initial condition, which by the way is a different initial condition than on your homework problem. the solution curve heads up this way before coming back around this way, and it approaches seemingly some curve that it looks like it's staying on as time goes by, as time increases, as t goes to infinity. And that curve that it seems to be approaching and perhaps staying on is called a periodic solution because it comes back to where it starts. Now, I purposely said seemingly approaches and stays on. It actually never touches the periodic solution because of uniqueness. Here's how I'm bringing in existence and uniqueness. The existence says that since this vector field, since these right-hand side functions are nice, they are continuous, they're also differentiable, and their derivatives are continuous. It's certainly a nice right-hand side function, certainly a nice vector field. That means solutions, first of all, will exist. And so we're not approximating nothing here. NDSolve is approximating a true solution. They're also unique, which in the context of autonomous systems like this means these curves can't touch each other. So if there is some periodic solution that I'll kind of sketch to look somewhat similar here, some sort of egg shape like this, if there are initial conditions that give you a solution curve that truly comes back to where you start, say you start right there, if there is such a solution, then this curve is actually never touching it. It's only approaching it. It's not a limiting value, but it's a limiting curve. A limit cycle, that's why it's sometimes called a limit cycle. Uniqueness would say they can't touch. But it gets so close you can't tell the difference. But that is interesting. You get a periodic solution. There's a periodic solution that you can prove exists. I have not proven it exists, but you can prove it exists. And it seems like, at least for this initial condition, that this solution curve is approaching it as t goes to infinity. And so it seemingly, in the end, approaches some periodic function. We can graph x and y's functions of time as well. I won't take the time to do that at the moment because I want to get the Euler's method. But those would be approaching periodic solutions as well.
So isn't spiraling ever closer to that periodic solution?
Yep, exactly. It gets closer and closer as time goes by. Never touches it, but it gets so close that you can't tell the difference. I also used NDSolve so that I could change the initial condition for this example. And I used the locator, so now I can move this initial condition around if I like and see how the solution curve changes. And it looks like as long as you're not at the origin, as long as your initial condition is not at the origin, it looks like the solution curve approaches that periodic solution, that attracting limit cycle as t goes to infinity. That seems to be what's happening. Now here it's going off seemingly away, but I bet it comes back. We would just have to let time go further. It probably goes way over here before coming back along this way. I bet that's what happens. I could test it by letting t go out further. I'm not going to take the time to do that. In the time we have remaining, still thinking about this example, let's talk about Euler's method. Euler's method in 2 dimensions is a pretty natural extension of Euler's method in 1 dimension. You've got an arbitrary differential equation that may or may not be autonomous. Let's write it in a non-autonomous fashion, in vector form like this. With some initial condition, y of 0 equals y sub 0, where that's an initial vector. Little x0, little y0. So that's an IVP. We want to approximate the unique solution of this IVP. It's going to be unique if f is nice. With Euler's method. Euler's method has geometric meaning that I'm not going to take the time to get into. The book discusses it. You should make sure you understand that. It's related to thinking about this is giving you velocity vectors for solution curves. In the extra video that I made, the supplementary video, I get into the details of thinking about it as a velocity vector. You come up with a system of recursive equations that looks basically just like the same as before, except the second one now is a vector equation instead of a scalar equation. but this has the exact same form as Euler's method did before. Being a vector equation in the second one here, you can write it as a system of two scalar equations. If this vector field has components little f and little g, which could depend on t, little f of t xy, little g of t xy, I could rewrite this one single vector equation as a system of scalar recursive equations like this. The first one for x and this one for y. And if you're going to implement it by hand or with a computer, you got to deal with little f and little g. It's probably you're going to want to think about it this way. How can it be done with Mathematica? In pretty much the same way we did before with nest list. And again, I know this is a little confusing about how this works. Last spring I made an extra video related to this. And I also made an extra handout, a reading assignment. I will make those available to you as well. I will post the extra reading assignment with an extra couple examples in it. And I'll give a link to the extra video that I made about a year ago, just related to this topic and related to that notebook, talking about how to use Mathematica and in particular nest list to implement Euler's method. I will do it here right now, though it does get confusing. We do have these functions defined. I've already entered these, so I will use those. I'm going to create a new function that I'm going to call a capital G. Picking capital G is an arbitrary choice. I just don't want to pick a little f, a little g, or a capital F. I want to pick something different than those. This function that I'm going to create is going to be what goes into nest list to implement this iteration scheme. Nest list can be used to iterate functions. As I showed you with Euler's method in chapter 1 before, I'm going to use a subscript of delta t here to specify the step size. And I need an underscore because I'm defining the function there. I'm going to think of the input of this function as being a list, keeping track of little t, little x, and little y. This is going to be a function of a list of 3 entries labeled little t, little x, little y. And it's this function that I want to iterate to implement Euler's method. But what is this function? And what does it mean to iterate it? Its output is 3-dimensional just like its input is 3-dimensional. A list of 3 entries. Essentially what I want to do is to the first entry, t, which you could think of as being tk, I want to add delta t to it. Whatever delta t happens to be. So the first entry in this function is t plus delta t. We did this before in chapter 1. Again, it's confusing, but when I iterate this part effectively, that just keeps adding delta t to the previous value t, to the tk, to get the next value t that we label tk plus 1. What about the second entry? I want to update the value of x according to this equation. Maybe one thing that's confusing here is you don't need the k's when you do it on Mathematica, whereas when you write it by hand, you write the k's. That might be one thing that's confusing here. I want to take the old value of x and add on delta x. This whole thing represents delta x, or maybe better, delta x sub k. Write it by hand. So I take the old value of x, come back over here, x, and I add delta x, but I can't type it in as a delta x because I want to calculate delta x along the way. That thing is delta x. X plus f of txy times delta t. That's going to take these preceding values of t, x, and y, you could think of them as tk, xk, and yk, multiply times delta t, and then add xk to get the next value of x sub k plus 1. It's iterating this function that does that process. I explained this with simpler examples also in the video and in the extra reading assignment. There's simpler examples in this list. For the sake of time, we kind of have to be satisfied with maybe not completely understanding everything here. For what the y equation, do the analogous thing. This is the function we iterate. So for example, if I wanted to pick delta t to be 0.5, I'd put a 0.5 in there. So I'm iterating g sub 0.5. I'm iterating g when delta t is 0.5. I need an initial condition, and I need my initial condition to be a three-dimensional list, because that's the entries for the function g. Three-dimensional. You almost always pick the initial value of t to be 0. Then pick the initial value of x and y. I could pick the same thing I think I had in the animation, negative 0.5, negative 0.5. And then I need to put another comma and the number of iterations. Maybe I'll just do 3 iterations. That's the syntax. What does it produce? Okay. I have a problem here. Does it not know what g is? Oh, that's because little f and little g in my example don't depend on g. So I need to get rid of those. I think that's the reason. Yep, that's the reason. My example is autonomous. It's not non-autonomous. So I didn't need the t in those. So what is this producing? It's producing a list of 4 points, the initial point of which represents the initial condition. When time is 0, x is negative 0.5, y is negative 0.5. The second point is when time is 0.5. X is negative 0.625, y is negative 0.275. The next one is when t is 1. X is this, y is this. Then when t is 1.5, x is this, y is this. The second and third entries in each of these lists represent your approximate values of x and y along the solution group. Final thing to show you here quick is it'd be nice to have some nice way to get rid of the times in here so you can just plot the x and y coordinates in an xy plane, the phase plane. It'd be nice to have a nice way to get rid of those times. And you'll see this in my extra stuff and in the solution key. You can get rid of those times. Let me call this EM for Euler's method. You can get rid of those times by a little trick in Mathematica. And call it EM no time. You can go through the EM list and drop the first entry of each of those. Drop, well, EM, EMs with the 2 inside double square brackets like that. We'll pick off the second entry, for example, of EM. By putting an I there, that's going to be an entry that changes then as I increases from 1 to the length of this list. This list has 4 entries in it. Drop, and then a 1 after the EM will delete the first entry. So when I type drop EM2, comma 1, that will create a list, just these 2 elements. It's going to drop that first one. It's going to drop the time. And by putting that inside table like this, and then letting I go from 1 to 4, it'll do that for all these lists of 3 entries. Your new list just has the x and y coordinates, no t in them. And you can use list plot to plot those dots and connect the dots. And you'll see that again in the solution key, as well as to some extent on the video. Okay? See you on Monday.